Understanding Physics, 3 volumes in 1, by Isaac Asimov. Volume 2, Light, Magnetism and Electricity. Chapter 1, Mechanism. The Newtonian View. In the first volume of this book, I dealt with energy in 3 forms: motion, kinetic energy, sound, and heat. As it turned out, sound and heat are forms of kinetic energy after all. In the case of sound, the atoms and molecules making up the air, or any other medium through which sound travels, move back and forth in an orderly manner. In this way, waves of compression and rarefaction spread out at a fixed velocity. See page 1 through 156. Heat, on the other hand, is associated with the random movement of the atoms and molecules making up any substance. The greater the average velocity of such movement, the greater the intensity of heat. See page 1 through 234. By the mid-19th century, the Scottish physicist James Clerk Maxwell, 1831 to 1879, and the Austrian physicist Ludwig Boltzmann, 1844 to 1906, had worked out in strict detail the interpretation of heat as random molecular movement, the kinetic theory of heat. It then became more tempting than ever to suspect that all phenomena in the universe could be analyzed as being based on matter in motion. According to this view, one might picture the universe as consisting of a vast number of parts, each part, if moving, affecting those neighboring parts with which it makes contact. This is exactly what we see, for instance, in a machine like an ordinary clock. One part of the clock affects another by the force of an expanding spring, by moving, interlocking gears, by levers, in short, by physical interconnections of all kinds. In other machines, such interconnections might consist of endless belts, pulleys, jets of water, and so on. On the submicroscopic scale, it is atoms and molecules that are in motion, and these interact by pushing each other when they collide. On the cosmic scale, it is the planets and stars that are in motion, and these interact with each other through gravitational influence. From the vast universe down to the tiniest components thereof, all might be looked on as obeying the same laws of mechanics, by physical interaction, as do the familiar machines of everyday life. This is the philosophy of mechanism, or the mechanistic interpretation of the universe. Gravitational influence does not quite fit this view, as I shall point out shortly. The interactions of matter and motion obey, first of all, the 3 laws of motion. See page volume 1, 23. Propounded by Isaac Newton, 1642 to 1727, in 1687, and the law of universal gravitation that he also propounded. The mechanistic view of the universe may therefore be spoken of, fairly enough, as the Newtonian view of the universe. The entire first volume of this book is devoted to the Newtonian view. It carries matters to the mid-19th century, when this view had overcome all obstacles and had gained strength until it seemed, indeed, triumphant and unshakable. In the first half of the 19th century, for instance, it had been found that Uranus traveled in its orbit in a way that could not be quite accounted for by Newton's law of universal gravitation. The discrepancy between Uranus's actual position in the 1840s and the one it was expected to have was tiny. Nevertheless, the mere existence of that discrepancy threatened to destroy the Newtonian fabric. 2 young astronomers, the Englishman John Couch Adams, 1819 to 1892, and the Frenchman Urbain Jean-Joseph Leverrier, 1811 to 1877, felt that the Newtonian view could not be wrong. The discrepancy had to be due to the existence of an unknown planet whose gravitational influence on Uranus was not being allowed for. Independently, they calculated where such a planet had to be located to account for the observed discrepancy in Uranus's motions, and reached about the same conclusion. In 1846, the postulated planet was searched for and found. After such a victory, who could doubt the usefulness of the Newtonian view of the universe? And yet, by the end of the century, the Newtonian view had been found to be merely an approximation. The universe was more complicated than it seemed. Broader and subtler explanations for its workings had to be found. Action at a distance. The beginnings of the collapse were already clearly in view during the very mid-19th century peak of Newtonianism. At least, the beginnings are clearly to be seen by us, a century later, with the advantage of hindsight. The serpent in the Newtonian Eden was something called action at a distance. If we consider matter in motion in the ordinary world about us, trying to penetrate neither up into the cosmically vast nor down into the submicroscopically small, it would seem that bodies interact by making contact. If you want to lift a boulder, you must touch it with your arms, or use a lever, one end of which touches the boulder while the other end touches your arms. To be sure, if you set a ball to rolling along the ground, it continues moving even after your arm no longer touches it, and this presented difficulties to the philosophers of ancient and medieval times. The Newtonian first law of motion removed the difficulty by assuming that only changes in velocity required the presence of a force. See page Volume 1, 24. If the rolling ball is to increase its velocity, it must be struck by a mallet, a foot, some object. It must make contact with something, material. Even rocket exhaust, driving backward and pushing the ball forward by Newton's third law of motion, makes material contact with the ball. Again, the rolling ball can be slowed by the friction of the ground it rolls on and touches, by the resistance of the air it rolls through and touches, or by the interposition of a blocking piece of matter that it must touch. Material contact can be carried from one place to another by matter in motion. I can stand at one end of the room and knock over a milk bottle at the other end by throwing a ball at it. I exert a force on the ball while making contact with it. Then, the ball exerts a force on the bottle while making contact with it. We have two contacts connected by motion. If the milk bottle is balanced precariously enough, I can knock it over by blowing at it. In that case, I throw air molecules at it, rather than a ball. But the principle is the same. Is it possible, then, for two bodies to interact without physical contact at all? In other words, can two bodies interact across a vacuum without any material bodies crossing that vacuum? Such action at a distance is very difficult to imagine. It is easy to feel it to be a manifest impossibility. The ancient Greek philosopher Aristotle, 384 to 322 BC, for instance, divined the nature of sound partly through a refusal to accept the possibility of action at a distance. Aristotle felt that one heard sounds across a gap of air because the vibrating object struck the neighboring portion of air, and that this portion of the air passed on the strike to the next portion, the process continuing until finally the ear was struck by the portion of the air next to itself. This is, roughly speaking, what does happen when sound waves travel through air or other conducting medium. On the basis of such an interpretation, Aristotle maintained that sound could not travel through a vacuum. In his day, mankind had no means of forming a vacuum. But 2,000 years later, when it became possible to produce fairly good vacuums, Aristotle was found to be correct. It might follow by similar arguments that all interactions that seem to be at a distance really consist of a series of subtle contacts, and that no interaction of any kind can take place across a vacuum. Until the 17th century, it was strongly believed that a vacuum did not exist in nature, but was merely a philosophical abstraction, so there seemed no way of testing this argument. In the 1640s, however, it became clear that the atmosphere could not be infinitely high. Indeed, it was possibly no more than a few dozen miles high, whereas the moon was 250,000 miles away, and other astronomical bodies were much farther still. Any interactions between the various astronomical bodies must therefore take place across vast stretches of vacuum. One such interaction was at once obvious, for light reaches us from the sun, which we now know is 93 million miles away. This light can affect the retina of the eye. It can affect the chemical reactions proceeding in plant tissue. Converted to heat, it can evaporate water and produce rain, warm air, and winds. Indeed, sunlight is the source of virtually all energy used by man. There is thus a great deal of interaction by light between the sun and the earth across the vast vacuum. Then, once Newton announced the law of universal gravitation in 1687, a second type of interaction was added. For each heavenly body was now understood to exert a gravitational force on all other bodies in the universe across endless stretches of vacuum. Where two bodies are relatively close, as are the Earth and the Moon, or the Earth and the Sun, the gravitational force is large indeed, and the two bodies are forced into a curved path about their common center of gravity. If one body is much larger than the other, this common center of gravity is virtually at the center of the larger body, which the smaller then circles. On the Earth itself, two additional ways of transmitting force across a vacuum were known. A magnet could draw iron to itself, and an electrically charged body could draw almost any light material to itself. One magnet could either attract or repel another. One electric charge could either attract or repel another. These attractions and repulsions could all be exerted freely across the best vacuum that could be produced. In the mid-19th century, then, 4 ways of transmitting force across a vacuum, and hence 4 possible varieties of action at a distance, were known: light, gravity, electricity, and magnetism. And yet the notion of action at a distance was as unacceptable to 19th century physicists as it had been to the philosophers of ancient Greece. There were 2 possible ways out of the dilemma, 2 ways of avoiding action at a distance. First, perhaps a vacuum was not really a vacuum. Quite clearly, a good vacuum contained so little ordinary matter that this matter could be ignored. But perhaps ordinary matter was not the only form of substance that could exist. Aristotle had suggested that the substance of the universe outside the earth itself was made up of something he called ether. The ether was retained in modern science even when virtually all other portions of Aristotelian physics had been found wanting and had been discarded. It was retained, however, in more sophisticated fashion. It made up the fabric of space, filling all that was considered vacuum, and, moreover, permeating into the innermost recesses of all ordinary matter. Newton had refused to commit himself as to how gravitation was transmitted from body to body across the void. Quote, "I make no hypotheses," he said austerely. His followers, however, pictured gravitation as making its way through the ether much as sound makes its way through air. The gravitational effect of a body would be expressed as a distortion of that part of the ether with which it made contact. This distortion would right itself, and in the process distort a neighboring portion of the ether. The traveling distortion would eventually reach another body and affect it. We can think of that traveling distortion as an ether wave. The second way out of the dilemma of action at a distance was to assume that forces that made themselves felt across a vacuum were actually crossing in the form of tiny projectiles. The projectiles might well be far too small to see, but they were there. Light, for instance, might consist of speeding particles that crossed the vacuum. In passing from the sun to the earth, they would make contact first with the sun and then with the earth, and there would be no true action at a distance at all, any more than in the case of a ball being thrown at a bottle. For 2 centuries after Newton, physicists vacillated between these 2 points of view: waves and particles. The former required an ether, the latter did not. This volume will be devoted in good part to the details of this vacillation between the 2 views. In the 18th century, the particle view was dominant. In the 19th, the wave view. Then, as the 20th century opened, a curious thing happened. The 2 views melted into each other and became one. To explain how this happened, let's begin with the first entity known to be capable of crossing a vacuum: light.